we have to solve this question. It says oxygen gas contained in a cylinder of volume V of 1 into 10 power minus 2 meter cube has a temperature T of 300 Kelvin and a pressure P of 2.5 in 10 power 5 Pascal. After that, some of the oxygen is used at constant temperature. The pressure falls to 1.3 in 10 power 5 Pascal. Find the mass of the oxygen gas used. So we had to find the mass of the oxygen gas used, but initial mass is also not given. So first I'll find the initial mass. We know from the equation of a state normal ideal gas, PV is equal to nRT. So I can say N will be equal to PV upon RT. So N1 will be equal to P1 V1 upon RT1. Now putting the values, N1, P1 is, pressure is 2.5 into 10 power 5, volume is 1 into 10 power minus 2, value of R is 8.313 and temperature is 300 Kelvin. So this is the N1, means number of molecules, and they come out to be 2.5 exponential 5 into 1 exponential minus 2 divided by 8.313 divided by 300. It comes out to be 1.0024. 1.002445. These are the number of moles. I will round it off in the end. Number of moles N1. Now let us find the N2. Again, N2 will be equal to P2 V2 upon nRT2. P2 is pressure falls to 1.3 into 10 power 5, and volume is same. Volume is same, 1 into 10 power minus 2 divided by it is P2 V2 upon RT2 only. So R is 8.313 into T2. Temperature is again same, 300 Kelvin. So 1.3 exponential 5 into 1 exponential minus 2 divided by 8.313 divided by 300. This is now 0.5213 moles. So actually this is the first moles when the pressure, this is the second mole. So how much oxygen used, number of moles of oxygen used, (1.002245) minus 0.5213. It comes out to be 0.4812 moles. Now these are the number of moles used. Why this is the number of moles used? I found what are the number of moles initially and what are number of moles of finally. Then I subtracted just this number from this one. So then this is the number of moles. So I have to find the volume of the mass of the oxygen gas used. So mass will be mass of oxygen used. It is 0.4812 multiplied by molar mass. Molar mass of oxygen is 32 into 10 power minus 2. You already know. Molar mass of the oxygen is that one. Why I have used this formula? You know, number of moles N is mass of the sample upon molar mass. So I had to find the mass of the sample. So mass of the sample must be, I have used this formula here, N is equal to mass of the sample upon molar mass. So mass of the sample will be just mass of the sample, MS is equal to N into M. So I'm just calculating M into N, this one. So into 32 exponential minus, it is minus 3, sorry, minus 3 coming out to be 0.0154 kg up to 3 significant figure. So this is the mass of the oxygen used. So let us see how we have found it again. First of all, I will use the formula PV is equal to nRT. First I found the number of moles in that one. Number of moles N1, P1 is 2.5 10 power 5 into V1 is 1 10 power minus 2. A value of R is 8.313 and temperature is 300. It comes out of this one, moles. Then I found the moles when the pressure drops. So moles then comes out with this one with the same formula with the change of value, only the value of P2 changes. The number of moles of oxygen used are this one. This minus this. These are number of moles. Now I can find how the mass of the oxygen gets used. Mass will be simply this moles number multiplied by molar mass. So I found this mass as this one. This is the second question. It says, sorry, a cylinder containing 19 kg of compressed air at a pressure of 9.5 times that of atmosphere is kept in a store at 7 degrees centigrade. Suppose this is a cylinder and this has a safety valve on it. This is the gas cylinder. Now this gas cylinder has 19 kg of air at a pressure of how much? At a pressure of 9.5 times of P naught, and there are mass of the gases. Now what happened? And its temperature is at 7 degrees centigrade. This is the first state. Now second time, now what happens? The pressure increases. When the pressure increases, the safety valve is open and some of the molecules escape from this. Now I don't know how much the volume is, the mass is left here, but volume will be same and pressure is, I can say 10 P naught and temperature is this one. So I can use the ratio method of the general gas equation. I can just say P1 V1 upon M1 T1 is equal to P2 V2 upon M2 T2. And I had to find a formula for air. I had to find the M2. I'll be bringing M2 here. So M2 P1 V1 T2 must be equal to M1 T1 into P2 V2. So M2 will be coming as M1 into T1 into P2 into V2 upon P1 into V1 into T2. Let us put the values now. M2. M1 is clearly 19. T1 is 7 degrees centigrade. 7 degrees centigrade Kelvin becomes 280.15. Actually, we always if it is suppose this temperature T1 is 7 degrees centigrade, I will add always 273.15 and it becomes 280.15 Kelvin. Our syllabus suggests that if you have to convert this centigrade to Kelvin, you have to add 273.15. So this 19 and 280.15 into P2. P2 is 10 times P naught into V2 is suppose V. P1 is 9.5 times P naught into V1 is V, and T2 is 27 degrees centigrade. I will add 273.15. It becomes 300.15. Now I have to calculate this, and if I this V cancel out with V, P naught is cancel out P naught. If I want to calculate this, (19) 280.15 divided by 9.5 divided by 300.15, it comes 18.66. It is coming 18.67 kg. So mass of the air remains in the cylinder is 18.6 kg, but he has asked how much mass has been escaped. So mass escaped is 19 minus 18.67, so it is 0.33 kg. So that's it. Let's again I'm explaining this question. He says there is a cylinder, okay, in which the air is there's a cylinder containing 90 of compressed air. The air is there. Air can be treated as a gas, its mass is 19 kg, its pressure is 9.5 times, and it is kept in a stored temperature of 7 degrees centigrade. Actually, when the pressure increases, there is a safety valve. It is released. It releases some number of molecules or number of moles or mass of the air, so the pressure is reduced, because when the number of moles are escaped or mass is released, then the pressure is also reduced and its temperature become 27 degree. So I use this one, P1 V1 upon M1, T1 is equal to P2 V2 upon M2 T2. I just make the subject matter M2 and it comes out to be this one, and I use these values. Why I have used V1, V2 as V and V1 as V? Because the volume doesn't change, the cylinder is same. You know already that volume of the gas is always the volume of the container. So volume of the container remains same, so volume will remain same, and P naught cancel out. So this is 18.67 kg. Now this is mass of the air, compressed air, which remains in the cylinder. So mass which has been escaped is 19.867. 19 minus 18.67, it comes out to be 0.33 kg. Now this is another question. It says there is a helium gas occupies a volume of 0.04 meter cube at a pressure of 2 into 10 power 5 Pascal and temperature 300 Kelvin. Calculate, number one, the mass of the helium. I have to calculate the mass of the helium and then the RMS speed of its molecules for this temperature and other things. A third is the RMS speed at 423 Kelvin when the gas is heated at constant pressure to this temperature, means this is the RMS speed of the helium gas at 423 Kelvin. Then he says the RMS speed of hydrogen molecules at 432 Kelvin. This is 423 Kelvin and this is 432 Kelvin. So let us see how we can tackle this problem. First, he has given the value. He says relative mass of hydrogen and helium is 2 gram per mole and 4 gram per mole. Actually 2 gram per mole will be 0.002 kg per mole, I can say, and this will be 0.004 kg per mole. I can write this also because this is in grams, so you can say in this way. Now for the first part, I will say, you know, the solution I am giving. For the first part, I can say PV is equal to nRT. So N is equal to PV upon RT. So pressure is 2 into 10 power 5 pascals. Volume is 0.04. Value of R is 8.313 into temperature is 300 Kelvin. So the volume comes out to be 2 into 2 into 2 exponent 5 into 0.054 divided by 8.313 multiplied by 300. It comes out to be 3.21 moles. 3.21 moles. So it's written in the unit mol, not moles. So this is N. Now I had to find the mass of the sample. We know N is mass of the sample upon molar mass. So mass of the sample is N into molar mass. So N is 3.21 into, this is helium, and helium has a molar mass of 0.004 kg. So it is 0.004. So this coming out to be 0.0128 kg, or I can say it is just the 12.8 grams. It's 12.8 grams, or it is 0.0128 kg or 12.8 grams. This is one answer for part 1. It's very simple. You can say PV is equal to nRT. So N comes out to be PV upon RT. Put the values. This is 3.21 mole. So now number of moles N is mass of the sample upon molar mass. So mass of the sample becomes number of moles into molar mass. Molar mass is 0.004. So this comes out to be this one. Now for the second part, I'm going to here second part. He says the RMS speed of its molecules. the RMS speed of molecules at this one, at this temperature. The temperature is given, so it's Vrms is equal to 3 RT upon m under the root. Second part, 3 into R is 8.313, temperature is 300, and molar mass of this is helium, so it is 0.004 under the root. And let us, I just give the answer in 3 significant figures. 3 into 8.313 into 300 divided by 0.004, square root of it. It comes out to be 1367. It's 1367 meters per second, but I will just give the answer 1370 meters per second. So RMS speed is that one. It's very simple. The second part, I can say Vrms is equal to 3 RT upon m under root. I put the values. M is the molar mass 0.004, and put the values, you get this one. Now for the third part, the third part says the RMS speed at 423 Kelvin when the gas is heated at constant pressure to this temperature. So again, this is for the third part. Vrms speed will be 3 RT upon m under the root. Same formula. So it's 3 into 8.313. Now temperature is 423 upon m is, this is again the helium, so it is 0.004. So again the same formula has been used, only you have to check the calculation. 3 into 8.313 into 423 divided by 0.004, and square root of this, it coming out to be 1623.9 or 24 meters per second. I can just quote 1620 meters per second. So the second part, third part, it's very easy. Vrms is equal to 3 RT upon m under root, and put the values and find it. Now the fourth part is, again you will be using the same formula for fourth part. Vrms is equal to 3 RT upon m under the root, but now this m will be for the hydrogen. This m will be for the hydrogen. So this is 3 into R is 8.313 into temperature is 432 now upon hydrogen is 0.002 molar mass of hydrogen. So take the square root of this one, and you can get just 3 into 8.313 into 432 divided by 0.002 under the root, and it is coming 2320 meters per second, 20.9. So you can just take this one. So this was just using the formula Vrms is equal to 3 RT upon m under